How can the SpaceX Raptor engine change so much in such a short time? I mean, it went from this, and now to this in just 10 years. Now, that might not sound particularly fast until you compare it with other rocket engines. The Space Shuttle main engine flew with essentially the same design for more than 30 years and is still being used on NASA's SLS rocket today. The RD-180 that powered the Atlas V is a derivative of an engine family first developed in the 1970s. Meanwhile, SpaceX has already gone through 3 major generations of Raptor in less than a decade, with each version dramatically better than the last. No known rocket engine program in aerospace history has evolved this quickly. So today, we'll break down the famous Raptor engine and explore how SpaceX simplified the design with each generation, making it lighter, more powerful, and easier to build. Back in 2012, Elon Musk described Raptor as the engine that would take SpaceX beyond the limitations of Falcon 9. But before you can build a revolutionary rocket engine, you first have to answer a surprisingly simple question. What fuel are you going to burn? Everything else comes after that. For SpaceX, this was an opportunity to solve one of the biggest challenges they were already running into with Falcon 9. Instead of burning kerosene and liquid oxygen like the Merlin engines, Raptor would use liquid methane and liquid oxygen. And that decision alone solves several problems at once. For starters, it burns much cleaner than kerosene. Merlin engines tend to accumulate soot after repeated firings, a little like how your kitchen gets dirty after cooking the same meal every day for a year. Methane, by comparison, produces almost no soot, making it far easier to inspect, maintain, and reuse engines. That's a pretty big advantage when your entire business plan revolves around not throwing rockets into the ocean after every flight. At the same time, methane avoids many of the frustrations that come with liquid hydrogen. Hydrogen offers fantastic performance, but it's also notoriously difficult to work with. The stuff is so small it seems determined to leak out of anything you put it in, turning routine engineering tasks into an ongoing battle against the laws of physics. SpaceX also decided to supercharge the performance of both propellants by chilling them below their normal boiling points, a process known as subcooling. This makes the liquids denser, allowing more fuel and oxidizer to fit into the same tanks. The result is surprisingly significant. Those denser propellants allow roughly 8 to 10% more mass to be loaded into the vehicle without making the tanks any larger. In the rocket business, where engineers fight for every fraction of a percent in performance, getting a free 10% boost is about as close as you'll ever get to finding money lying on the sidewalk. Unlike Merlin's relatively simple gas generator cycle, Raptor uses what's called a full-flow staged combustion cycle, one of the most complicated rocket engine designs ever attempted. Even NASA's Space Shuttle main engines, now known as the RS-25s flying on the Space Launch System, use a less complex version of staged combustion. The phrase full-flow staged combustion sounds like something you'd hear in a graduate-level engineering class right before deciding to switch majors, but the concept is surprisingly elegant. Every drop of methane and oxygen passes through the engine's preburners before reaching the main combustion chamber. Nothing gets dumped overboard. Nothing is wasted. Raptor has 2 separate preburners. One creates hot methane-rich gas, while the other creates hot oxygen-rich gas. These gases spin massive turbopumps that pull even more propellant from the tanks. In a sense, the engine powers itself. It's basically using controlled explosions to run the machinery needed for bigger controlled explosions, which is peak rocket engineering. After powering the turbopumps, the hot gases flow into the main combustion chamber, where they are carefully mixed using swirl injectors. There, they burn at pressures approaching 300 bar, among the highest ever achieved in an operational rocket engine. That's roughly equivalent to the pressure found several kilometers beneath the ocean, except it's happening inside a metal chamber that's also on fire. Interestingly, Raptor doesn't burn methane and oxygen in perfectly balanced amounts. Instead, it deliberately uses excess oxygen. According to Musk, getting too close to the ideal chemical ratio would simply melt the engine. And while turning your rocket into a puddle of expensive metal is certainly one way to increase performance, it's generally considered bad for reusability. Finally, the superheated exhaust blasts through the nozzle at enormous speed, producing the thrust needed to lift Starship toward orbit. Of course, none of this comes easy. In fact, Raptor is arguably one of the most difficult rocket engines ever attempted. It's the kind of project that makes aerospace engineers stare at whiteboards for hours and then suddenly decide they need another coffee. In fact, no flyable, full-flow, staged combustion engine had successfully reached operational service before Raptor. The closest example was the Soviet RD-270 from the 1960s, but that program was canceled before it ever flew. So SpaceX wasn't just building a new engine. In many ways, they were trying to finish a homework assignment that had been sitting unfinished for over half a century. One of the biggest headaches involved the oxygen-rich side of the engine. Hot oxygen is surprisingly aggressive. Most metals would rather not spend their day being blasted by high-pressure, oxygen-rich gas at extreme temperatures. Engineers had to develop specialized materials like SX500, capable of enduring over 800 bar so it could survive conditions that easily destroy conventional hardware. Testing reflected just how difficult this challenge was. Early preburner experiments at NASA's Stennis Space Center and later tests at SpaceX facilities required years of refinement before the engine could operate reliably. Getting the propellant flows, ignition sequence, temperatures, pressures, and turbopumps all working together was a bit like trying to conduct an orchestra where every musician is holding a flamethrower. Even after the first full-duration hot fire in 2016, the work was far from over. Engineers continued fighting vibration issues, durability concerns, and unexpected resonances. At one point, early Raptors developed a 600 Hz vibration mode that shook parts of the engine in ways engineers definitely did not appreciate. Rocket engines are already controlled explosions. The goal is to keep them controlled. Then there was combustion stability. When you're mixing methane and oxygen as hot gases at extremely high pressures, even small instabilities can rapidly become very expensive problems. The injector design had to be carefully tuned to prevent destructive pressure waves from forming inside the chamber. As if designing the engine wasn't hard enough, SpaceX then ran into an entirely different problem: actually building enough of them. In late 2021, Elon Musk reportedly warned employees that Raptor production had become a full-blown crisis. Starship needs a lot of engines. The Super Heavy booster alone uses 33 Raptors, and the upper stage needs several more. Suddenly, building a handful of engines every month wasn't good enough. SpaceX needed production rates approaching 1 engine per day. That's the sort of manufacturing challenge that sounds reasonable until you remember that each Raptor is basically a controlled explosion wrapped in some of the most advanced turbo machinery ever built. The engine's complexity became its own enemy. Every Raptor contains dual preburners, dual turbopumps, thousands of precision-machined components, and hardware designed to survive temperatures and pressures that most engineering textbooks would classify as good luck. Even tiny manufacturing errors could create major problems. Some components required tolerances measured in single-digit micrometers. To put that into perspective, a human hair is roughly 70 micrometers thick. Engineers were trying to manufacture critical rocket hardware with tolerances so small that a speck of dust could feel personally involved. Then there were the materials. Raptor relies on specialized high-temperature superalloys capable of surviving brutal operating conditions. Unfortunately, aerospace-grade materials don't magically appear when you need them. Supply chains had to be expanded, suppliers had to be qualified, and production lines had to be adapted. It's hard to build hundreds of rocket engines when you're still waiting for parts that can survive being inside a rocket engine. And even if all the materials arrive on time, you still need people who know what to do with them. SpaceX had to recruit and train machinists, welders, inspectors, and technicians capable of working with cryogenic systems and extremely demanding aerospace standards. You can't exactly hire someone on Monday and have them building flight-ready Raptor engines by Friday. When you look at the history of Raptor, you start to realize something interesting. The reason SpaceX iterated the engine so aggressively may not have been just because they wanted to. In many ways, they had to. The engine was simply too complex to get right on the first try. Every new version revealed problems that nobody could fully predict beforehand. Components wore out faster than expected. Manufacturing processes need refinement. Vibration issues appeared. Costs were too high. Production rates were too slow. Reliability wasn't where it needed to be. Each problem demanded another redesign, another round of testing, another hardware swap, and another lesson learned. From the outside, it can sometimes look like SpaceX was changing the engine constantly. But when you're trying to mass-produce one of the most ambitious rocket engines ever built, constant iteration isn't necessarily a sign that something is wrong. It's often the only way forward. So, what exactly has changed about Raptor over the years? Raptor 1 was all about proving the impossible. This was SpaceX's first operational, methane-fueled, full-flow staged combustion engine, a sentence that would have sounded insane to many rocket engineers back in 2012. The goal wasn't simply to build a better Merlin to create an engine capable of powering a fully reusable spacecraft system. After years of development and testing, Raptor finally achieved its first full-duration hot fire in 2016. That was a major milestone because, up until that point, full-flow staged combustion engines were mostly things that existed in research papers and canceled Soviet programs. By 2019, Raptor 1 finally got its chance to fly aboard Starhopper. If you've forgotten what Starhopper looked like, imagine someone turned a grain silo into a spacecraft and then somehow made it fly. Against all odds, it worked. The engine produced roughly 185 tons of thrust and delivered impressive efficiency. But it wasn't exactly production-friendly. It relied heavily on 3D-printed components, contained a large number of parts, and was relatively heavy and complicated. It proved the concept worked, but it also revealed just how much work remained. In many ways, Raptor 1 was less of a finished product and more of a flying engineering laboratory. By the time Raptor 2 arrived in late 2021, SpaceX had learned a painful but valuable lesson. Building one incredibly advanced rocket engine is hard. Building hundreds of them is much harder. So, instead of chasing maximum performance, SpaceX focused on something far less glamorous: simplification. Engineers aggressively removed components, reduced plumbing, consolidated systems, and redesigned major sections of the engine to be easier to manufacture and more reliable in service. Elon Musk often says that the best part is no part, and Raptor 2 looked like an attempt to test that philosophy on every component that wasn't absolutely necessary. The ignition system was simplified, valve assemblies were integrated, sensors and plumbing were reduced, manufacturing methods were redesigned around large-scale production rather than prototype construction. The result was an engine that was simultaneously lighter, more powerful, and easier to build. Mass dropped from roughly 2,000 kilograms to around 1,630 kilograms. Chamber pressure climbed to around 300 bar, among the highest ever achieved by an operational rocket engine. Thrust increased to approximately 230 tons. Most importantly, Raptor 2 was built with production in mind. Because a Starship fleet doesn't need a handful of perfect engines, it needs thousands of engines that can be built quickly, flown repeatedly, and maintained without causing engineers to lose sleep every night. This focus on simplification worked so well that by the time Raptor 3 came along, SpaceX decided to double down and simplify the engine even further. At first glance, the engine almost looks unfinished. Much of the external plumbing, shielding, and hardware that covered earlier Raptors has disappeared. But that's exactly the point. Rather than adding more systems, SpaceX integrated many of them directly into the engine itself. The plumbing became cleaner. The structure became simpler. The number of exposed components was dramatically reduced. It's a bit like opening the hood of a modern car and realizing half the parts you expected to see aren't there anymore because engineers found ways to combine them. The performance gains are equally impressive. Raptor 3 produces around 250 tons of thrust at sea level, while vacuum engines produce 275 tons of thrust, 606,000 pounds force, up from 258 tons. Yet despite that increase, the engine is actually lighter, weighing around 1,525 kilograms. The engine's thrust-to-weight ratio now exceeds 180, making it one of the most powerful and efficient rocket engines ever built. Perhaps the most remarkable change is what isn't there. Thanks to improved regenerative cooling, Raptor 3 no longer requires much of the external heat shielding that earlier versions needed. Some fire suppression systems have also been eliminated because there are simply fewer hot external surfaces to worry about. The result is an engine that is more powerful, lighter, easier to manufacture, and potentially more reliable than anything that came before it. And that's really the pattern you see throughout SpaceX's development process. The first version demonstrates that something is possible. The second version makes it practical. The third version starts turning it into a system that can support real-world operations. Whether Raptor 3 ultimately becomes the final version of the engine remains to be seen. If SpaceX's history has taught us anything, it's that the answer is probably absolutely not. In fact, Elon Musk has already hinted at what comes next. While future Raptor 3 variants may push toward 300 tons of thrust, Musk has stated that Raptor 4 will almost certainly cross that milestone. That might sound like a small improvement until you realize we're talking about a rocket engine that already produces enough power to launch a small building into the sky. If those goals are achieved, future super heavy boosters could generate more than 10,000 tons of thrust at liftoff. For comparison, the Saturn V that carried astronauts to the moon produced about 3,400 tons. In other words, SpaceX isn't just trying to build a bigger rocket. They're trying to build something that makes the biggest rockets of the Apollo era look surprisingly modest. And that's really the story of Raptor as a whole. When people hear about higher chamber pressures, improved thrust-to-weight ratios, and advanced manufacturing techniques, it's easy to get lost in the technical details. But all of those improvements serve a much larger goal: making access to space dramatically cheaper. For most of spaceflight history, rockets have been treated like disposable airplanes. Imagine boarding a Boeing 747 for a flight from New York to London, then watching the airline throw the entire aircraft into the ocean after landing. That's essentially how the launch industry has operated for decades. Not surprisingly, that approach gets expensive. Raptor was designed from the very beginning to change that equation. Its methane fuel burns cleaner than kerosene, reducing maintenance between flights. Its full-flow staged combustion cycle extracts more performance from every kilogram of propellant. And its architecture is specifically optimized for repeated reuse, rather than a single glorious trip followed by retirement at the bottom of the Atlantic. The result is Starship, a vehicle that could eventually place more than 100 tons into orbit while being flown again and again. If SpaceX succeeds, the cost of reaching orbit could fall by an order of magnitude compared with traditional launch systems. That has consequences far beyond SpaceX. Lower launch costs mean more satellites, more scientific missions, more space stations, more opportunities for industries that currently exist only as PowerPoint presentations and ambitious conference speeches. Things like orbital manufacturing, large-scale space telescopes, and even space tourism become much easier when launching cargo doesn't cost a small fortune every time. It's no coincidence that competitors have been paying close attention. Companies like Blue Origin, Rocket Lab, and others are increasingly pursuing reusable rockets of their own. Even traditional launch providers have been forced to rethink their long-term strategies. Whether they like it or not, Raptor and Starship are helping push the entire industry toward reusable spaceflight. But perhaps the most important reason SpaceX made Raptor has nothing to do with Earth. It has everything to do with Mars. Methane and oxygen can potentially be produced on Mars using local resources. Carbon dioxide from the Martian atmosphere can be combined with hydrogen extracted from water ice to create methane fuel through a process known as the Sabatier reaction. That means future crews wouldn't necessarily have to bring all of their return fuel from Earth. Instead, they could manufacture it after landing. This is one of those ideas that sounds like science fiction right up until you realize engineers have been studying it for decades. Without some form of local propellant production, establishing a permanent presence on Mars becomes extraordinarily difficult. With it, Mars starts looking less like a one-way destination and more like a place where regular transportation might eventually be possible. That's why Raptor matters. Yes, it's an impressive rocket engine. Yes, its chamber pressures are absurd. Yes, the turbopumps spin at speeds that would make your car engine immediately explode. But those are just engineering details. The bigger picture is that Raptor represents an attempt to move spaceflight from an era of scarcity to an era of abundance. From a handful of launches each year to potentially hundreds. From rockets that fly once to rockets that fly again and again. From missions that visit other worlds to missions that might one day stay there. Whether Starship ultimately succeeds remains an open question. Space is still hard, physics is still unforgiving, and history is littered with ambitious aerospace projects that looked unstoppable until reality intervened. But if humanity ever does establish cities on Mars, there's a decent chance historians will look back at Raptor the same way we look at the steam engine today. Not as the final version of the technology, but as the machine that made an entirely new era possible.